Good morning, everyone. Welcome to my talk, Demystifying Point Authentication on Apple 1. My name is Zechao. Currently, I'm a master's student at Zhejiang University. I will share our research work on point authentication hardware software on Apple 1. Here's the outline of my talk. First, I will introduce what is PAC and the current research state of Apple's PAC. And then I will introduce our motivation and contributions. Finally, I will share our findings on Apple's PAC protection, including Apple's PAC hardware software implementation and our analysis of PAC protection on Apple 1. So let's start with what is point authentication. Point authentication, or PAC, is a hardware feature introduced in ARMv8.3 specification. It was designed to safeguard the integrity of pointers from pointer corruption attacks. Pointer authentication provides PAC instruction to sign the pointer. PAC instruction will take three inputs, the key, pointer, and modifier. And then it will sign the pointer by generating a signature and storing it to the higher unused bits of the pointer. To illustrate the practical application of pointer authentication, let's take a look at a simple example. Typically, pointers are stored in memory and later loaded out for function call or memory access. Therefore, attackers often target this pointer. By crafting the pointer, they can hijack the control flow or data flow for further attack. To mitigate such an attack, we can use pointer authentication by signing a pointer before it is stored in memory. With pointer authentication, if the attacker tries to craft the pointer, that will be detected by all the instructions. Note that even the PAC or the signature is also stored in memory. The attacker cannot forgery a valid signature because they don't know the key. In the real world, Apple was the first one to implement and deploy pointer authentication in their devices. Since 2018, this hardware-based mitigation has proven to be effective and practical against pointer corruption attacks. As a result, there has been a huge decrease in public asynchronous exploits, such as jailbreak exploits. Therefore, there are a lot of research work has been done on Apple's PAC protection. However, most of them are focused on software or how to bypass PAC protection. In contrast, there's only one research work has mentioned the hardware side. It's the work done by Brendan Azad from Google Project Zero. And Brendan discovered that Apple customized the pointer authentication hardware to achieve cross-EL and cross-key attack mitigation. And these attacks or cross-domain attack mitigation cannot be defended by ARM-spec pointer authentication. However, the exact implementation detail of Apple's cross-domain attack mitigation remain unknown to researchers outside of Apple. As a result, previous works on analyzing Apple's PAC software are not comprehensive. So that's our motivation. Currently, there's no systematic analysis of the Apple's PAC hardware software implementation. So we conduct a systematic analysis of this significant hardware-based protection. More specifically, we reverse engineer the Apple PAC hardware software implementation. And then we conduct a security analysis of PAC protection on Apple 1. And here are our contributions. First, to analyze the PAC hardware and software implementation on Apple 1. We built up a reverse engineering framework based on an open source hypervisor called Mini. And secondly, we successfully disclosed how Apple customized the pointer authentication to achieve cross-domain attack mitigation. While Brendan's work is disclosed cross-EL and cross-key attacks, we further expand the analysis to include two additional cross-domain attacks, the cross-boot attack and cross-VM attack. And lastly, we have conducted a comprehensive security analysis of Apple's PAC protection. We identified 4 attack surfaces within the latest SU kernel. Our findings are publicly acknowledged by Apple. Apple fixed these issues in a security update and assigned us a CVE. So let's head into the next part, the Mini-based reverse engineering framework. The framework requires 4 capabilities to analyze the Apple's PAC hardware and software. The first required capability is to identify Apple-specific PAC-related system registers. To achieve this capability, the challenge is that Apple introduced a lot of new registers to control Apple-specific CPU features. However, there's no official documentation on these registers. So we need to identify the Apple-specific system registers for pointer authentication. Our key observation is that although Apple did not disclose the source code or documentation about these registers, we can identify them based on the information from binary and system register redirection feature. And finally, we can confirm the result by verifying whether the register can impact the PAC instruction behavior. For the second required capability, the challenge is that we discover Apple implements a hardware PAC key protection. To analyze Apple's PAC hardware, we must bypass this protection to read and write the key value used for signature generation. This challenge is the most difficult one for PAC hardware analysis. We found that this protection is deployed on both EL1 and EL2 exception level. For both of them, we propose 2 different techniques to bypass it. For the EL1 key protection, our basic idea is to read and write the key from the higher exception level. For the EL2 key protection, our solution is to read and write the key value before the Apple PAC is enabled. For the required capability 3, the challenge is that the interface between registers and instructions are complex. We need an effective method to analyze the PAC instruction behavior on 8.1. Our solution contains 3 steps. Step 1 is to set up the registers, including control registers and key registers. Note that these registers are identified based on the first required capability of the framework. Step 2 is to use the ability powered by our second capability to read or write the key value. And the final step is to run the PAC instruction in different domains, such as virtual machine and host machine, user space, and kernel space. For the final required capability, the challenge is that we want to analyze and debug the SM kernel dynamically during kernel boots. However, the official kernel debugger LDB does not support active kernel debugging. To achieve this required capability, we build up a hypervisor-based kernel debugger based on the mini hypervisor. More specifically, we replace the instructions in macOS with hypercore instructions to implement breakpoints. And then we handle the exceptions in the hypervisor to implement a debugger. Based on this reverse engineering framework, we successfully disclosed Apple's PAC hardware software implementation and conducted a security analysis of this hardware-based protection. So here are our findings. For Apple's PAC hardware, we disclosed Apple's PAC hardware design. Our findings include controllability, PAC algorithm, and cross-domain attack mitigation. For the first part, we discovered Apple introduced a new control register, APCTL, and also Apple implements a customized PAC algorithm instead of the Karma algorithm recommended by ARM. For the cross-domain attack mitigation, we formalized the attack model in our paper, and then we analyzed the Apple's PAC hardware under this attack model. For detail about the formulation, please check our paper. So here we can see that there are 4 types of cross-domain attacks, and we disclose how Apple mitigates these attacks by customizing the pointer authentication hardware. The first one is cross-VM attack mitigation. We discovered that Apple introduced a key transformation when setting up the higher 64-bit of the PAC key. At the same time, Apple introduced a new 128-bit register, VMDiff, to diversify the key transformation between your virtual machine and host machine. The second one is cross-key attack mitigation. we found that Apple introduced a per key type sorts to differentiate the key transformation for different key types. More importantly, the result of the VM-diff XOR with per key type sorts will be one of the inputs for key transformation. The third one is cross-boot attack mitigation. We confirmed that Apple introduced per boot diversifier to differentiate the key transformation for different CPU boots. The final one is cross-EL attack mitigation. Apple introduced a extra key, and which is used for XOR with AP keys, such as API-A, API-B, etc. And the result will be one of the inputs for pack algorithm. The extra key can be enabled in user space or kernel space. And then we found that the SM kernel only enables it in user space. As a result, the signature generated in user space and kernel space are different. For the pack software or the PA-based kernel protection, we analyzed the sign-out interfaces and key management. For the sign-out interfaces, we analyzed all pack instructions in the SM kernel. Our findings show that the latest implementation of sign-out interfaces is far more complex than official documentation. For the key management, first, we reverse engineer how the SM kernel configures the keys, and then combining our findings on Apple's pack hardware, we summarize the key management implementation in the SM kernel. The results show that Apple implements a fine-grained key management based on customized pack hardware. Finally, we conducted a security analysis of the pack protection on FM1. We identify and validate 4 attack surfaces. And we validate 88 cases that can be used to bypass the PA-based kernel protection. And Apple acknowledged our finding publicly and fixed these issues in a security update and assigned us a CVE. And thank you. Thank you for having me. And this is our work. If you are interested in more detail, please check out our paper. And now it's for Q&A.